Compiler construction number 8. So we're now going to expand our language yet again. And this time we're basically going to introduce booleans, things that consume booleans, and things that produce booleans. One of the consequences of using booleans is that now there's going to be two kinds of values in our program. They're either going to be numbers or booleans. So that's going to mean that we're going to have a type system to check to make sure that we're doing things correctly. So we're going to call our new language R2. And R2 looks like the following. So our expressions will be everything that we had before, except that we'll have a few new stuff. We'll have true, which is the true constant. We'll have false, which is the false constant. And then we'll have a bunch of operations that combine booleans. So we'll have and of 2 e's, we'll have or of 2 e's, and we'll have not of 1 e. Next, what we'll do is we'll have comparison operations that consume numbers and produce e's. And we're going to have a category of comparisons. Then we're also going to have if statements, which are really if expressions that look at a boolean and determine which of two expressions we'll evaluate. And then finally, we're going to add subtraction. Now, the comparison operations are their own set of things, which are equality. So equality, we have less than or equal to, greater than or equal to, and greater than. And now we're going to introduce a new category called type. And types in this language are either signed 64-bit numbers, that's what we've been using so far, or bools. Right? So this is our new language. Now every time we make the language bigger, that now causes everything else to change in the language. Really, everything else to change in the compiler. We have to slowly bridge down into all of the other things. Yeah. Now, one thing that you could do, by the way, actually, hold on. Yeah, so we're going to have to change every little piece of our system. So we're going to have to change our interpreter. We're going to have to change, RCO, all those things. What I recommend that you do in your compiler is you update your data type, and then then make your program, compile and type checker or whatever, and just make it so that in all the parts of the program that don't yet support these things, you just throw an error. And then what that'll do is it'll make it so you can identify places that you need to update as you see those errors occur. Now, there's sort of two things that we want to talk about next. We want to talk about how to extend the interpreter and how to enforce the type system. And I want to make a little note that we can actually simplify and, or, not, and subtraction into other things if we want. So what do I mean by that? I mean that and xy is always the same as if x. So if x is true, then return what y is, otherwise return false. And or xy is always the same as if x is true, then return true, otherwise return y. And not x is always the same as if x false, true. And then subtraction of xy is always equal to the addition of x and the negation of y. So if you want to, you could actually implement the R2 language by adding true, false, comparisons, and if, and ignoring and, or, not, and subtract. And just make it so that all of these things just become different kinds of if statements. And that is totally acceptable to do that. And in fact, I would actually kind of recommend doing that because it's going to simplify your compiler. But we're going to like give ourselves the opportunity to think about R2 programs as being made up of all these features. But if we really want to, we can have like, you can kind of think of it as like, this is what the E language is, but we can sort of have like an E prime, and this is going to be what the compiler actually sees, and that would be the same things that it used to be, then true, false, the comparison of two E's, and then an if statement of two E's. And if you wanted to, you could actually just focus on compiling this thing because and, or, not, and subtract are really the same as those. Okay, that out of the way. Let's talk about how to interpret this language. So remember that, hold on one second. Just fiddling with my notes. But the notes are on the computer, and it's super slow from recording. All right. Okay. So the interpreter, what it does is it takes a program and returns an answer. Okay. Well, the set of answers in our language is now bigger. It used to be that it was just a number, and then now it's a number or a bool. Similarly, our programs used to be R1, and then, sorry, our programs used to be R1, and then now they're R2. Everything is going to be just the same as it used to be with our interpreter. Our interpreter has an environment, and it has the program, or the expression, and we just have to explain what happens with the new stuff. So true, of course, becomes true, and when we interpret false, we get back false. When we interpret an if statement that has an expression for the condition, an expression for the true, and an expression for the false, what we do there is we're going to interpret in the environment k, where k is equal to an if statement in our like normal programming language. So we're going to actually run if, and we're going to say if interpret in the environment the condition C. Then we're going to return ET. Otherwise, we're going to return EF. So the idea is that you're going to interpret the condition expression, get the answer, look at it. If it's a true, you use ET. Otherwise, you do EF, and then you interpret whatever that one is. And then finally, we need the comparison operations. So if we have a comparison operator that has, which particular operation that we want to do, and then the expression on the left and the expression on the right, well, what we're going to do there is we're going to do whatever the actual operation is. So we're going to interpret the environment, the expression on the left, and then do the operation with the interpretation of the environment on the right. Now, when I say do the operation, what I mean is that like, if it's an equal sign, then we do equal. If it's a less than, we do less than, etc. I'm not going to explain how to do that because you know how to do that. Like, you have the language you're using, you can just call the number equality. All right. Now, the thing is that this new language that we have has two different kinds of values, right? And you can write programs that don't make sense. So we can write a program, let me just put a little bar right here. We can write a program like +1 true. And this program doesn't make any sense. Now, if you ran this program in C, it would return 2. And why would it return 2? Because most C compilers make it so that true is really just an abbreviation of 1. But you don't want to do that. You don't want to be a filthy animal. So, similarly, another error would be something like, not of 5. Now, why would not of 5 be an error? Well, remember, what is not? So not really means that we have an if of 5, and then a false here, and a true here. That's what not really means. And so this is an error because that spot right there is not a bool. Okay? So that's why not 5 would be an error. Another example of an error would be something like an and of true and 5. Now, why is that an error? Well, remember, what is this thing? It's the same as if true, then return 5, otherwise return false. Now, why is this an error? It's an error because these two things don't match. Don't match. Another example of an error would be something like less than of 5 and true. This is an error because that true right there is not a number. So yeah, not a number. So what we do is we write a function that is called type C that takes an expression and returns what its type is, or errors. And errors, of course, if there is no type. So those expressions I showed before, they would be an error. Now, because our program has variables, that means that we really need to have another argument, which is a mapping from variables to their type. And we call this the environment, the type environment. By tradition, we write the definition of type C in the following form. We write gamma proves that E has type T. And this means that type C of gamma and E should equal type. Now, it means that it should equal that. But just kind of as an aside, there are ways of writing type systems using this notation that do not easily correspond to programs. So for example, we could write the following. We would write gamma proves that true has type bool, or gamma proves that false has type bool, or gamma proves that a number n has type S64. So these are all basic statements about what the type C program should return. And they correspond to, in the actual type C program, not looking at gamma and seeing if it's true and just returning bool. The reason that this notation is useful is because for when we look at a rule like the addition rule. So for instance, here's the addition rule. It says that gamma proves that if EL has type S64 and gamma proves that ER has type S64, then we can conclude, which we write as a bar, that gamma proves that plus of an EL and an ER has type S64. Now, this notation right there corresponds to a kind of complicated program. It corresponds to the following program. It corresponds to type C of gamma and an add node where we have an EL and an ER. This is going to be equal to, let the type of L be equal to type C gamma of EL, and let the type of R be equal to type C gamma of ER. And then what we're going to do is we're going to say something like, do a case analysis on the type of the left, and if we get S64, then do a case analysis on the type of the right, and if we get S64, then return S64, and otherwise error, and otherwise error. So this two-line notation means this complicated program where we look at both things, we look at the corresponding types and we check them, and then we choose the appropriate side. So this notation is much more convenient to use than writing this long program, and that's why we use it. So we have to say what happens for addition, which we just did, for true, false, for numbers. We also have to say what happens for lets, variables, subtraction, comparisons, and ifs. So here is the rule for subtraction says that gamma proves, so if gamma proves that EL has type S64, then gamma proves that the negation of EL has type S64. Okay, so we got addition, subtraction, numbers. Okay, so we want variables, lets, and ifs. So ifs have the following rule. We say that, a little fleck there, that gamma proves that if of EC, ET, EF has type, if gamma proves that EC has type bool, and gamma proves that ET has type T, and gamma proves that EF has type T, then that means that we return type T. Now think about what this means as a program. It means you see that there's an if statement, and you call the type checker on EC. Then you check to see if it's a bool. Then you call the type checker on ET and EF, and you check to make sure whatever those two things are, they're the same. And then once you know that they're the same, you return whatever they are. Okay, so this is the thing. So this right here protects against us doing, not 5. And the fact that we're matching these protects against saying, and 5 and 2. All right, the last thing are variables. And notice that so far, we've never actually looked at gamma. We've never looked at the type environment. And that's what variables are going to be for. We're going to have a rule that says that gamma proves that a variable x has type gamma of x. So what this means is that when you see a variable, you look up inside of the type environment whether or not it has one, and then if it has a type, then you return that. Otherwise, of course, you error because it's not in the list. Okay, then what would you do other than that? Other than that, we would say, for let, we would say gamma proves that let x equal xe in be has type tb if gamma proves that xe has type tx and gamma extended with a mapping from x to tx proves that be has type tb. So what this is doing is it's saying that we look at the let position and we first check to see the expression and we see if it has some type. We don't know what type it is, we just check to see what it is. So once we know that it has a type, then we take that type and we record it inside of the type environment, and then we type check be. And after type checking be, we see that it has some type, and that's the type that we return. Now, this notation of writing down the type checker makes use of the fact that gamma is like an input position. The expression in the middle is like another input position, and then the right-hand side, the type, is like an output position where the type is always determined by the other two things. There are type systems where that's not possible, and we'll actually see that in the future of this class, but not right now. And in those situations, we this notation fails a little bit at describing what an algorithm would do. And so this mapping of this notation to programs, you can't do that mechanically on all times that you will ever see this notation in your life. Okay, so now we have the interpreter and the type checker. If you don't run the type checker, the interpreter could make a mistake because, for instance, you could run one of these programs right here and get a nonsense thing to happen inside of your interpreter. So that means that our interpreter can actually error, but once a program passes our type checker, it is guaranteed not to error. That is actually an interesting theoretical result that's called type soundness. That is a really important thing to study, which is why we talked about it in the Organization of Programming Languages course. But we're going to ignore that for now. For now, what we're going to do is we're just going to assume that all programs that we write do type check, and of course, include in your compiler a check to make sure that this actually happens. Okay, now the next thing that we need to do is we need to we need to update our random generation program. Because remember, the way that our random generation program worked before is that it would, just randomly generate some program. But now, what we would like to do is we'd like to constrain our random generation program to generate programs that are guaranteed to type check. Now, why do we want to do this? Of course, it would be useful to check programs that don't type check, you know what I mean, to make sure that our type checker really works. However, the point of our random checking program is so that we can find errors in our compiler. That's the point of it. And our compiler won't run if the type checker fails. So that means that if we're going to generate 1,000 random programs, and all the ones that don't type check won't be useful for finding errors later in the compiler. So they're not really useful, you know what I mean? And it turns out that it's really hard to randomly generate a program that type checks accidentally. Because remember how the type checker worked. Sorry, the random program generator worked. It was the randp function, and it took as an argument a set of variables, which were the variables that it had defined previously. And then it took a number, and then it returned an expression. And then when you call randp with some set of variables and 0, what it would do is it would randomly pick one of a number, or it would choose a variable reference. Or it would choose read. And it would choose these randomly. Now, let's imagine that what we do is we just add in an additional case that's for a bool right here. If we add an additional case for a bool, and what we do is we generate an addition. Well, that means that we're going to have to generate 2 subprograms, one on the left and one on the right. Now, the one on the left, if it generates a number or a read, then it's going to type check. So let's say that half of the time it's going to type check. But if it generates a bool, it will fail. And if it generates a variable reference, it will generate an error whenever that variable reference refers to a boolean. So let's say that half of the variables refer to booleans and half of them refer to numbers. In that case, the probability of succeeding is going to be 1/4 for the number plus 1/4 for the read plus 1/8 for the amount of time that we'll get the variable reference. So that right there is, I'm doing math live, it's dangerous. So that's going to be 5/8 of the time we're going to get something that actually type checks when we get a number. But of course, getting a number requires us to do 2, right? Because we got to do one on the left and one on the right. So that means that to get the probability of doing it right, we have to multiply those together. So we're going to get, 5.5 squared, right? And so that's just the probability of getting a number correct. So if we do, 25 divided by 64, the probability of us generating a single addition correctly is 40%. So this right here is about 40%. So this is just for generating a single addition correctly. So the probability of using kind of like a naive random generation algorithm to get the right answer is very unlikely. So what that means is that we have to make our random program generator sensitive to what kind of type it's going to generate. And so what we're going to do is we're going to structure it in the following way. Oops. So randp is going to take a number and return an expression. And what it's going to do is it's going to call a helper function. So randp of n is going to call another function that's called rande, and it'll take in an empty mapping, and it'll take in a type. So we're going to randomly choose S64 or bool, and then it's going to take in n. Now what rande does is rande takes a mapping from a type to a set of variables. And it takes in a type, and it takes in a number, and it returns an e. In this e, it promises we'll have that type. That's the idea. Now rand e, we'll call this thing right here sigma. So rand e, if you give it sigma, and you give it the type bool, and we get a 0, well then that means we have to generate a 0 depth program that is a bool. So that means that we can generate either a true, or a false, or we can generate a variable, which is one of the variables inside of sigma bool. So we'll look inside of sigma, look inside of the bool thing, and choose one of those variables. Now, here's kind of a little bit of a subtle point. If there are no variables, then we're not allowed to have this be one of our options. So you can't like flip a coin, so you can't roll a d3, like a 3-sided thing, and choose either true, false, or a variable if there are actually no variables. So what you first need to do is you need to say, are there variables? If there are, then choose one of 3 options. Otherwise, choose true, false, or a variable. And maybe you might want to make it so that you might want to play with structuring this randomness. Okay, so what if we get a number and a 0? Well, in that case, we can do what we did before, where we either generate an actual number, or we'll generate read, or we'll generate one of the variables inside of sigma 64. And we'll use the same logic, as I just mentioned, that there may not actually be any variables. Okay? Well, now we can think about the more interesting cases. What happens if we call random generation on a bool and n+1? What are the different choices there? Well, what we can do is we can either generate a comparison operation. So we could generate a compare. And compare is going to take rand e of sigma s64 and n, and then another rand e sigma s64 and n. And of course, we'll choose this randomly. We'll choose which comparison operation it's going to be randomly. Let me just put a little note right here, random. Okay, that's one way to get a Boolean that is structured. Another way to get a Boolean that's structured would be to do let x equal rand e sigma, and then here we'll get a random type, n, inside of a rand e with sigma, this type, which is bool, and n. So what we could do is we could randomly make a new variable. And when we randomly make a new variable, that variable could be anything. And actually, it turns out that this sigma would actually be expanded to sigma prime, where sigma prime is equal to sigma, except that whatever type that is, we'll call that xt. Let's put a little note right here, xt, where xt gets updated to be sigma xt union x. So we're going to add one thing to that set. So we can either make a comparison, we can make a let, or we could generate a fresh if statement. This is option 1, this is option 2. Option 3 to generate a Boolean was that we could have an if statement. An if statement would be an if where we have a rand e with sigma, bool, and n. And then we could also have a rand e sigma, bool, and n, and then another rand e sigma, bool, and n. So the idea here is that we have 3 different ways. We can either do a comparison, a let, or an if statement. And these if statements, their results have to be Booleans. So this is the case for Booleans. What is the case for, What is the case for when we call rand E with sigma and an S64 and n plus 1? Well, there are similarly, 3 different possibilities. We could do option number 1, which is that we could do an addition of a rand E of sigma, S64, and n, and another rand E sigma, S64, and n. Okay. We could also do a let. So we could do let x equal rand E sigma, and then we'll write here xt for some random type, n, inside of rand E sigma extended with a mapping from xt to sigma xt union x, and then S64 and n, where xt is some random type. And then 3, we could generate an if statement. So if we generate an if, what here we would have is a rand E of sigma bool n, and then we would have on the other sides a rand E sigma S64 of n, and rand E sigma S64 of n. So now notice that there are these 2 rules that are in common, the let rule and the if rule for both cases, but S64s have the ability to generate a plus, and bools have the ability to generate a comparison. And notice that you can sort of flip-flop between them. What I mean by that is that if you start off trying to generate a number, well, you can generate a bool by generating an if statement, or by generating an x that has that type. Similarly, if you start off generating a bool, you can generate a number by trying to generate a comparison, or by generating a let, where the random type is a number. So what this means is that now our random program generators can generate programs that return an arbitrary type, and it will always return a program that is correctly typed. Cool. Next, let's talk about the next part of our system, which is our optimizer. So remember, the job of the optimizer is to take an R program and return another R program. And of course, this will be R2 programs. So the question that we should ask is, what kind of optimizations are even possible with this language? So, of course, if you're given a concrete true or false, we can't optimize that. So we'll say that, bools are, simple, so don't optimize them. So don't optimize. But remember that we had this idea inside of our optimizer where we'd look at the thing being bound to a let and say, is this thing simple or complicated? And things that were simple were other variables and numbers. Well, Booleans are simple. So those things, if you see a let that mentions a concrete bool, it should flow down into it. What are other things that we can do? Well, if we have a comparison and we give it 2 concrete numbers, then we can reduce that to a value. Reduce to value. So we can actually perform whatever the operation is and really do it. Similarly, if we get an if statement that has a concrete bool in it, then what we can do is we can reduce that to either ET or EF. So we can concretely look at this statement and just reduce it to whatever it's supposed to be. What other operations can we do? Well, here's something that you might think that we could do. We could do something like, if you saw a knot of E, if you saw a knot of E, then you could turn that into just E. So that is a good optimization that we can think about. However, here's a question. Remember, we're going to imagine that knots are desugared into if statements. So what that means is that this is really another way of writing if some expression E, false, true, false, true. Now how could we turn that thing into just E? Of course, it's true that we could turn it into E, but how could we imagine how to figure out that we can turn it into E? That's the more complicated thing. Another thing to think about is, so how can I do that? Obviously, if E is a constant, it would get reduced away. Let's talk about this later when we actually talk about writing the algorithm. But this is the kind of thing that we would like to be able to do. Here's another thing that we might like to be able to do. We might like to be able to do something like, if you have an if and then a not of E with some true branch and some false branch, then we would like to turn this into just an if of the E with the false branch and the true branches swapped. Because that way, this by the way is an F, let me make it really obvious that it's an F by having a really curly thing, because what an not does is it kind of like undoes them. So think about how we could think about that here. So here there's a not inside of there, and so if you switched the F and the T there, then you would then realize that that the if doesn't do anything. And what am I trying to say by that? So here's like another rule. If we had an if of an E with then true and then false, then we could reduce that to just E, because it the if doesn't do anything. That E must have been a Boolean in the first place. So we can remove the if from the program altogether. Okay. So, why is that relevant? Well, if we're like analyzing an if statement, so these are just some ideas. Okay, now, what are other things that we could try to do? There are some comparisons that we could imagine optimizing away. For instance, suppose that we had an equality of E1 and E1, then we could imagine reducing that to true. But that would only be possible if E1 had no reads in it. Now what I mean by having no reads in it is that if we literally look at E1 and we see whether or not there's any read expressions. Because if there are read expressions, then just because there's a read over here, it doesn't mean it's the same value as the read over there. But in contrast, if this was like x plus 2 and this was x plus 3, sorry, x plus 2 and this is also x plus 2, then we know that those are going to be the same no matter what x is. Okay. So, with all of these ideas in mind, here's actually another thing that we could think about. We could think about turning, a less than of E1 and then an addition of some concrete number n and E1. We could imagine turning that into true if n is greater than 0. So there's all these optimizations that we could imagine doing. And you should come up with a few of them. Yeah. And by the way, this whole thing about not, like, this might be a case for why it would be bad to do that desugaring that I talked about if you can't figure out a way to optimize them away, having them desugared into the if. So these are some things to think about. Okay, so here's Let me mention one more that we might want to do. Another one that we might want to do is imagine that we have an if statement and there's some condition and then some expression that appears on both branches, like the sides are identical. If the sides are identical, then in that case, what we could do is we could turn this into just a let of some variable that we don't care about equal to c inside of E1. Because we know that no matter what happens, we're always going to return that E1. So if the two expressions are identical, in this case, we can do this even if they're impure, because we know that only one of them will be evaluated. All right. Oh yeah, and there's one last kind of cool thing that we can do. Imagine that we had an if statement that where the condition was an expression like x. And then we had ET and then EF. Well, in this case, what we could do is we could actually turn this into an if statement where we have that x there, but then we take ET and we find all of the x's and replace them with true. And then we find all the f's. Sorry, when we go in EF and we find all of those x's and replace them with false. The idea here is that because we know that this if statement tells us that this expression x is true or false, we can use that information in the rest of the program. And this substitution right here is the key to thinking about how to get rid of these knots. Basically, what we could try to do is make it so that when you optimize, you don't just reduce this one expression into a value, or into something else. What you really do is you determine more information about it, about the expression, like what it tells you about the values of other variables. And if you learn something about those other variables through the operation, then you can figure out what the value must have been. Another example of this is that when we're doing the optimization, we could do something like the following. This is 8 and 9, I believe. We could do something like the following. Like imagine that we're looking at a let statement. So x is equal to xe inside of be. What we could do is we could figure out what variables be uses. And if be doesn't use x, then we could just sequence it by not binding it to anything. And if it does get used, then but if xe is pure, then we can just totally throw it out because it's not actually needed in the rest of the program. So we can think about that like something like this. So imagine that we're calling optimize on this. What we would do is we'd say something like, so let me put let with a capital L to distinguish it from let inside of the program language we're writing the optimizer in. So we could say, let's let the new version of xe, which we'll call xe prime, and then we'll also keep track of whether it's pure, so we'll call that xe, dash pure question mark. And then we'll also have xe vars, which are the variables used inside of this expression. And we're going to have this equal to the optimization of xe. Then what we're going to do is we're going to let, let's say that there's this argument called sigma, which just stores information about the context that we're doing optimization in. And then we'll say that we'll let sigma prime be equal to sigma, where x is mapped to xe prime if xe prime is pure. If xe prime is pure, and then otherwise we'll just have it be actually x. And then what we'll do is we'll say that be prime and be pure and be vars is what we get by calling the optimizer on sigma prime and be. And then we'll all do this inside of something where we're going to say if x is not inside of be vars, that means that we don't actually even look at it. Then what we're going to do is we're going to say that if it's pure, then we're just going to return be prime, be pure, and be vars. Because we don't look at it and it's pure, so therefore we don't even need to care about it. Otherwise, what we'll do is we'll turn it into, a let underscore equals xe prime in be prime. This means that we don't observe the value, but we still have to include it. And then, of course, that's what our new expression is, but we have to return whether it's pure. In this case, it would not be pure, so we would return false. And the reason is we know that xe prime is not is not pure, so that means that this whole thing is not pure. And the things that we look at would be the be variables unioned with the xe variables. And then otherwise, if it was mentioned, then in that case, we would return a let of an x equals, this is a capital let, by the way, let equals xe prime in be prime, and then the purity would be the and of be pure and xe pure. And then the variables would be the be variables subtracted, where we remove x, and then we union the xe variables. And so this right here would be an example of a way to think about increasing the amount of information that the optimizer gives. It would tell us the expression, whether it's pure, and what variables it mentions. And what we could do is we could have it so that to implement something like this down here, we could have it also include, so of course you can implement this directly, but to implement something like this, you could have it say something like, here's the information that you would know if this thing were true, and here's the information that you would know if this thing were false. And you might know something like, well, if this expression right here were false, then I would know that E must have been true. And here I would know that E must have been false. And then you could then use that to do this, switching transformation right here. So basically what I'm telling you is there are lots of optimizations that you could do in this language. It's much more advanced than the other one, and you should do some of those. At the very least, you should do the partial evaluation of the Boolean operations. You should remove ifs that have known values, and you should substitute variables. You should do that variable substitution thing. And if you build in not, then you should definitely remove wrappers of those. You should flip them, the cases. And another thing that you could do is this whole if thing right here with x's. If it's a not and then something, well then you just reduce it one time, and then basically it allows you to do the flipping. And then once you do the flipping, then you can apply this rule. What I'm saying is that if you want to do if not x, et, ef, then you could turn this into first if x, ef, et, then turn that into into if x, where we have e false, we find all the x's and replace it with true, and then et, and you find all the x's and replace it with false. And you would get this by doing first the not flipping case, then the variable substitution case. So at the very least, you should do those optimizations, and you should think about how much more effort you want to spend doing this, because it's pretty exciting, all the different things that you could do. All right. Okay. You're going to update your Uniquify pass, and the new features that we added to the language don't really change Uniquify in any meaningful way. All right. So now, what should we do next? The next thing that we need to do is we need to talk about how to update the C language and the transformations that work on C. And actually, you know what? I think we're at a good stopping point. Let's do that next time. So, see you later.